second law of thermodynamics can be stated two ways. Two different people stated these different ideas, and it turns out that mathematically we figured out later that they're saying the same thing. First, the Clausius statement says that no process is possible whose sole result is a transfer of heat from a body of lower temperature to a body of higher temperature. In other words, heat never transfers from a cold object to a hot object. It always goes the opposite way. So spontaneously, heat never goes from low to high temperature. The Kelvin statement is a bit more complicated than that. Kelvin's statement says that no machine can be made that only absorbs energy by heat and then entirely transfers the energy out of the engine by an equal amount of work. In other words, there's no such machine, and the machine part is important. There is no machine that can only take in heat and do work alone. And the reason that a machine cannot is because it is a cyclic process. There are some circumstances where something can absorb heat and only do work, but not if it's going to be cyclic. Let's figure out why. So let's say we have a piston perhaps in your car, and we have a gas inside this piston, and through combustion it pushes the piston out. So the fuel inside this piston explodes, combusts, and it pushes this piston outward. And so this is what's then being transferred into rotational energy to turn your tires on your car. Now the issue is we want to turn the tires again. After turning them once, you need to turn them a second time. So we have to get the piston to move back inward. In order to make the piston move back inward, we must remove energy. So right now we have a high energy fluid, a high energy gas, and so we must remove energy to get it back to its original conditions. So the reason that we must always have a coolant system in a car like your radiator is so that we can always return to our original conditions to do the process over again. And that's because a machine is a cyclic process. So to do the process again, we must remove heat to get back to our original conditions. We must get back to the same pressure, volume, and temperature. And that's going to take removing heat in order to do so. Another application, another type of situation that we can refer to talk about this is for a power plant. Now in a power plant, we have some kind of a container that has water in it, and we're boiling this water. Essentially, a power plant is a giant teapot. And so we boil this water, which produces steam, and so the steam travels up a pipe, and then it's going to be connected to a turbine, which is just a giant fan. So the steam now turns the turbine, turns that giant fan, that generator, and the problem is now we have steam, but we need to do the process over again. We're soon going to run out of water. So in order to get water back, we're going to have to cool it down. And so what we do is we take this water and we run it through a river. So we might have some kind of a cooling tower here, like at 3 Mile Island at TMI here, which is right near the Susquehanna River. And so we'll pull in some water from the Susquehanna River and we'll cool that water down, which produces steam. So really the only thing coming out of those cooling towers is steam. It's not any toxic waste or anything like that. So we cool it down, and now we get back to our water that we can boil again. So again, we need a cooling system in order to get back to our original conditions, and therefore we need to remove energy. So going back to our statement, the Kelvin statement, we cannot have a machine, we cannot have a cyclic process that only takes in heat and only produces work. We must remove some energy in order to get back to our original conditions to do the process all over again. Now, when we talk about that there's no such thing as just giving heat and just getting work out, we're saying essentially with the second law of thermodynamics, we're talking about efficiency. And so efficiency is a ratio of what you get out to what you put in. And with any kind of machine, we're getting out work and we're putting in heat. And the second law says that these two values are never equal. And so therefore we always have less than 100% efficiency. even if we have zero friction. We must have less than 100% efficiency. Now, using the first law of thermodynamics, which says that the total heat transferred, the heat added minus the heat removed, is equal to the work plus the change in internal energy. But a machine is a cyclic process. So for a cyclic process, the change in internal energy is zero. And therefore, the work is equal to the difference in the heat added and removed. So now replacing the work with the heat added minus the heat removed, we can get a new formula, which is divide each one by QH, and so we have 1 minus QC over QH. Because this cannot be zero, because we always must remove energy in order to get back to original conditions, we again can explain that we always have less than 100% efficiency. Now, the best type of engine you'll ever get is a theoretical engine called a Carnot engine. It's French, so the T is not pronounced. So a Carnot engine is 2 adiabatic and 2 isothermal processes. Again, it's theoretical. It's not that you build such an engine. And so the best efficiency you can ever get is actually 1 minus the absolute temperature at the colder reservoir, so this would be like the temperature of the radiator, divided by the absolute temperature at the hot reservoir, so this would be like the temperature of the combustion. Or if you want to go back to our power plant example, this is the temperature of the Susquehanna River, and this is the temperature of the boiling water. So what we have is that we're talking about there is an upper limit to the efficiency. There's a best efficiency that you can ever get. To make things more efficient, you want to make this ratio as large as possible. Get the colder reservoir as cold as you can, get the hotter reservoir as hot as you can, and this will eventually reduce your efficiency. So the second law of thermodynamics, heat never goes spontaneously from cold to hot. There is no machine that can only get out work when you put in heat because it has to be cyclic. We must remove energy to get back to original conditions. And this means that the efficiency is always less than 100%.